Okay, so today I'm going to talk about Factorial ANOVA, which is very similar to ANOVA, which I mentioned in the past where we did a one-way ANOVA. Now we're going to do a two-way ANOVA, which necessitates the terminology Factorial ANOVA because we have more than one factor. So in our case, we have, with my data set, which we will view in a couple seconds here, we do have two categorical predictor variables as well as a continuous outcome variable, and those two predictor variables have two levels, each into themselves, so that would necessitate a Factorial ANOVA approach. So what can Factorial ANOVA do? Well, we can assess more than one factor, multiple levels of those factors too, and then the means with them. So it's a little more complex than a one-way ANOVA, just one or more added levels and factors as well. And how does it work? Well, we're assessing means across multiple factors and levels, so that's what's going on behind the scenes, and that has to do with the breakdown of variances and squares. And to do that, which we will assess in a little, there are multiple assumptions that we need to meet, and a couple that are a little different from the common assumptions of regular ANOVA are the normality residuals, which I guess does apply to ANOVA as well. But then we also have homeoscedasticity, which in some terms, depending on how you look at it, can be very, very similar or synonymous to homogeneity of variance, but we will assess that in a couple rounds. And furthermore, we do have a couple more assumptions that I believe I covered. The last one was multicollinearity, and that can be assessed depending on what you have going on in a couple different ways. Now we'll talk about that later. So those are the major assumptions. So now we're going to move on to a hypothetical experiment that I'm doing with randomized data that would necessitate a Factorial ANOVA approach. So in my setting, we're saying that we have two different groups. We're creating two different module situations, a training module with job incumbents, and we're randomizing them and placing them into these two different groups. And then, let's say 6 months down the road, we take supervisory ratings, and now we're going to look at the difference in mean supervisory ratings across the different stipulations of where they were placed, and also if they did or did not pass the training module, which will become those that did or did not pass will become a level of our predictor variables or independent variables, if you will. Okay, so now we're going to move on to my code. So here we're going to read Excel, just the read Excel package, so we're going to open that. And then we're going to specify where my data is located, and that's the location within my computer, so we're going to open that and then view that, so we can take a brief peruse at my data, and that also produces a variable in my environment. As you can see, Module 2 and Module 1, as I was talking about, the supervisory rating. We can order those if we want to, just to get a general picture of what's going on, but we'll have better depictions in a little bit about what's going on with that. So now we're going to move on to the car package, as well as the PPS package, ggplot, molcom, pastex, and sjstats. Then we're going to use the attach function to point R towards this data set. We could specify that in our code, but I had previous issues with that, so we're just going to use the attach function out of necessity. And these packages do various things. For example, car, we're going to use that to do the Levene-Stats ggplot. That will be involved in our graph plots that we produce. And pastex, we're looking at effects.as sjstats. It's a general stats package. So now we're going to move on to this. So as you can see here, we're using the push function to create a new variable in our environment called module 1. And what we're going to do is we're going to factor that. And if we want to reference this, we're going to factor this. If we hover over this, we can see it's a numeric variable, but we want to produce a categorical predictor variable. So we're going to use the factor function, and we're going to have a couple specifications in here. We're going to point this towards our data set, and within our data set we're going to point R towards module 1, and we're going to use the levels function to say 1:2. That means we do have two levels, and we're going to pair that with the labels function, and we're going to specify a list here, yes and no. So that's going to point the 1 and 2 here towards yes and no. And that will, like it says here, create a factor, module 1. And we're going to do the same exact thing in this line and create module 2. As you can see, they both pop up into the environment. And now we're going to create a data frame that includes both of those things. We're going to call that dataset 2. And we're going to click on that just to take a look at it. In a rule of thumb, if you want to check whether you are successful in factoring your variables, you're going to hover over that, and it does say factor with 2 levels, and that's exactly what I wanted to convert it to yes and no. Same here as well. And then we have our outcome variable, Factorial ANOVA supervisory rating. It's a little bit funky of a name, but we're just going to go with it. Okay, and now we're going to do some descriptive statistics with the by function. And we're looking at here, we're going to be looking at module 1 and supervisory rating. So I'm going to go ahead and run these, and we can talk about what we're looking for a little later. But as a rule of thumb, it's a little better to make judgments about actually what's going on with more robust testing. But the by function does allow you to kind of get a better viewpoint of your variables, look at some summary statistics and things like that. So as I talked about before, we need to double check for homogeneity of variance, and we're going to do that by using the Levine's test. And here we're going to specify dataset 2, which is our dataset. And within that, your Factorial ANOVA supervisory rating, which is our predictor. And again, dataset 2, module 1, which is our first predictor variable. And I apologize if I just refer that as the predictor. I'm not sure if I did, but that is actually our outcome variable. And then we're going to center on the median, which is our robust measure of central tendency in our case. And so that's going to produce that. And again, I'm going to come back to our Levine's test and different outputs later and talk about what we want to look for in those. So I'm going to go ahead and run all the Levine's tests. And what I do want to mention here is we're going to also take into account the interaction of our two IVs and their levels here. So we're going to specify the interaction term within these brackets here. So that is the only difference with what's going on here. We're doing all the different combinations that we can possibly think of, and as well as their interaction. So we're going to run those. And they are all spitting out output for us. So now we're going to set the stage for a couple functions that we're going to do a little later, and we're going to do that by setting contrast. So we're going to use the contrast function, dataset 2, module 1, and we have the cbind function. This isn't necessarily necessary to use, but I personally prefer using the cbind function. And what we're going to do is we're going to set our contrast similar to what we did with the ANOVA, and that's going to set our contrast for the variables. And just to get a view of what we did here, we're going to double check our contrast here. So it's quite simple, our experimental setup, because we're only looking at essentially 2 levels. And a general heuristic is when we look at our factors here, where you can view them as negative versus positive. That's the contrast that is occurring. So these are not arbitrary assignments of our variables, well, our levels rather, but we are telling R to, for example, compare this chunk of variance to this chunk of variance, and those will correspond to our variables, so negative versus positive. And a very important thing is that these will add up to 0 when you add them, and they do in both cases. So now we're going to fit a model, and we're going to call that model 1 here, as you can see, AOB function, which is very similar to a linear model function. And we're just going to fit a model here, and we're going to want to specify an interaction term as well. So here we have our outcome variable and both of our predictor variables, and also we want to specify the interaction here, so we're going to do module 1 colon module 2, and that's specifying an interaction that we are interested in looking at. And again, dataset 2. So let's run that. Now we have our model produced, and what we're going to do is we're going to run a type 3 ANOVA, pay attention to the capital A here, on type 3 sum of squares rather, on model 1. And that's going to produce an output for us. And what we're going to do now is produce a linear model output of what we just did. And now we can get a linear understanding of what's going on. And I will come back to that, and we can decipher that in a couple minutes here. So now, just to get a little graphic depiction of what's going on in terms of assumptions and things of that nature, now that we have produced our model, we're going to want to check that out. It's a little funky here. We have the plot function, the model 1, the model that I just created. We're going to specify that. And it wants us to press return to view those, and those will pop up here. And a big thing that you want to look at here is kind of the, I guess the general shape of our plot here. And what you're looking for in terms of assumptions is that we're going to be wanting to look at a funnel plot here. Sorry, if the plot does look like a funnel, and it does not look like any of our variables are funneling around. So we're going to check that off as passing of the homogeneity variance. And now we're going to move on to the next one. And we're mainly interested in these first two plots for our purposes. And here we're going to be looking at the normality of residuals. And it looks like we generally do pass that assumption because a general rule of thumb is, hey, do our points hover around this line here that is produced? And they do. They're adhering pretty well to that. So we did pass that. And I'm just going to scroll through these next graphs here. And like I said, we're more interested in those. And now just to get another graphical depiction of what's going on here, we're going to use a bar chart, and we're going to push that into what we're going to call bar, and use the ggplot package, which we had opened earlier, and that is a visual data visualization package in R. So we're going to specify dataset 2, and then AS, that means aesthetics. So that's just kind of manipulating what's going on here. We're specifying our x variable. That did pop up. It kind of gives you, I guess it's not going to pop up again, but R does assist you in creating different functions by showing you a preview of, hey, what should go where. But in our case, we're using the first predictor variable here in module 1, and then we have our outcome variable, and we have supervisory rating. So that is our outcome variable. And we're going to do fill equals module 2, and that's going to push that into a bar graph. I'm going to run the next line here, and that's going to produce our bar graph. So this is a little difficult to read, but we kind of want to go through a chain of events here. And as I told you, I had two modules, so we're going to look at the X label, which I specified here. Did we pass module 1? Yes. So in other words, all of these people passed module 1. Now we're going to want to refer to this part. Did you pass module 2? And as we can see by the colors, purple corresponds to yes and yellow corresponds to no. So we're going to look at that. And basically the best thing to do here is get a general rule of thumb. Do we have an interaction? And by doing that, we're going to want to look at the differing levels of our IVs and according to their differing levels of their output. And they are all generally similar, but we don't want to, if I were a gambling man, I wouldn't want to gamble on a graphical depiction. I would want to look at the numbers, which we will do soon. And we will talk about those. But our interaction term was listed here. And we will go over that in a little. So, yeah, we did produce a bar graph here. Position has to do with the dodge, and that has to do with we're going to double check. The help bar is very helpful within R, if I can spell that correctly. Yeah, essentially what we're doing here is we're specifying that we want to place both of our variables on the same graph here, both of our IVs on the same graph, and that's what we're doing with the dodge function. And we're specifying here that we would like error bars, and we're using position dodge to specify that as well. And these are just kind of arbitrary assignations that I did with the sizing of the graph. And here we have our labels. Pass module 1, that's our X label. Y variable here, Y label there, and fill. Pass module 2, and that's going to label our legend there. So now we're going to move on. Hypothetically, if we did have significance in a significant interaction rather as well, we're going to want to look at simple effects to deduce more about what's going on. Spoiler, we did not have significance, but I'm going to go over that anyway. So now we're going to create dataset simple 2. We're going to specify here 4 and 7 because I do have 28 observations. And this is going to generate a single factor. And I will talk about that in a second when we can have a visual representation of what I'm actually doing here. and we're going to do that once as well, and we're going to specify a list 1 through 4, and we're going to create different labels for our list, and I will show you what this produces in 1 second. But essentially what we're doing is we're combining both of our IVs, or our predictor variables rather, into a single factor, and then we're creating labels for that. So if we want to reference our data set here, we have a little bit different of a different environment going here. Now we have a simple column, because I did create that, and we have a combination of both of these factors here into one factor. Yes, yes. So as you can see, if we look at different combinations of what's going on, it is reflected into our new one. For example, no, yes. That is now reflected in our simple column here in the singular factor. And now we're going to move on, and we're going to break down the groups into contrast, because that's what a simple effect does. And we're going to specify those as module 1f for effect and module 2f for effect. And very similar to the contrast function that we did earlier, we're going to create a list, and we're going to create we're going to assign them to different contrasts. Again, negative versus positive. We want them to add up to 0, and it looks like they do in all cases. And I believe I was on contrast 3, because we do have 3 contrasts that we're going to run. And now we're going to merge these 3 new variables into one object. Looks like I have a typo there. And that object's going to be called simple effect. And now what we're going to do is we're going to set the contrast to be this object. And then we're going to create a model to reflect what's going on here. And supervisory is going to be predicted by simple, as you can see by this enye there, which isn't the correct terminology, but I'm going to call it that. And yeah, we're having both of the effects coded of the IVs. Now we're going to create a linear model for that, and we can kind of view the significance of our simple effects, and we will reference that later. So after all that, we're going to want to get an idea of what our effect size was, and to do that we're going to do omega squared in our case. So we're going to specify omega factorial as the function that we're going to push all of these things into. And essentially what we're doing here is we're going to create a function, and we're going to tell R, hey, we want to be able to plug in values for these variables that are specified within this larger function here. We're going to want to do that a little later. So we're going to run that all, and I can explain a little bit more about what's going on. So within our first 4 lines, we're going to want to compute the mean squares, and we're doing that by dividing by the degrees of freedom in all these cases in the first 4 lines. And in the next ones here, we're pushing into variable A, variable B, and variable AB, as well as variable total. And essentially what we're doing is we're computing variance estimates about the equations above. And then down here we're saying, hey, I want to print the results of what's going on here. And that will happen in a second after we run this. And now we're going to specify, hey, these values, I want to plug these, as we said here, I want to plug these into the equation. And that's going to produce our omega squared. And as you can see here, we have our omega squared function. And in all 3 cases of our contrast. So now what we're going to do is we're going to go through our output here, and I'm just going to give a brief explanation about what you want to look for, and in our case what it means. So then we have our first output here, which is our basic summary statistics. And what I'm mainly interested here is we're going to look at means, and we have different levels. So this was our first production of our summary statistics. So we're going to look at the means, and we don't see too much variation, just eyeballing it between these different levels. We have, for example, module 1 yes, module 2 no. Module 1 no. So we don't see too much of a difference between those, but we cannot make significance judgments yet. Now here we have module 2 yes, module 2 no. Again, comparable means nothing substantially different. And now this function here, we're essentially creating a list, so that's going to produce where are we at here? Right here, and that's going to produce. We're producing a list here to look at different combinations. We're going to kind of group those. Yes, yes, for example. And then we have our means here. no, no, yes, no. So we're looking at different combinations of our predictors and their levels as well. So now we're going to look at the Levene's output, and the big thing here is we're going to want to look at the p-value, or rather the significance of the f-value that we have achieved. And the big thing with homogeneity variance, the assumption is, hey, is our test significant? If it is, in this case we don't want it to be significant because that would violate the assumption, but we seem to be good in all 3 cases. All 4 cases rather, where we haven't achieved significance, so we can say that we have passed that assumption test. So I'm going to scroll down here. Now we're going to look at the Type 3 ANOVA that we did produce, and what we're mainly interested here is we have main effects and we have the interaction effect. Main effect of module 1, not significant, not significant, and now this signifies the interaction effect, which was not significant either. So now we're going to move on to this, and what we want to do here is, now we're looking at our linear model output, linear model summary rather, of our model 1, and what I wanted to do was, and we do have similar output here, but what I wanted to look at was the p-value as well as the adjusted r-squared, and that can point us in the direction of multicollinearity, the assumption that I mentioned. For our case, you're going to be wanting to look at these 2 things here, and we have a pretty weak r-squared and a pretty insignificant p-value. Now if you did have a very powerful, strong r-squared rather, and a significant p-value, that would point you in the direction that, hey, we possibly have multicollinearity. We're going to want to do some further assumptions, and the way that you can do that, which I will not do in our case because I don't need to worry about that in my case, but you can produce what is called a correlation matrix, and from there you're going to want to look at what's called a VIF function, and that the VIF function will produce a number, and as you approach a higher number, as a general rule of thumb, and that stands for variance inflation factor. As you produce a higher number, you do have a higher possibility of violating that assumption of multicollinearity. Okay, so now we're going to look at our simple effects here, and what we're interested in is the significance values of the outputs here in the models we created, and we have not achieved any significance. We have fairly high p-values, so we can comfortably say that we do not have any simple effects, which would make sense because we do not have a significant interaction. And our last output here is omega squared, and as expected, due to our non-significant findings, largely, we don't really expect a powerful effect size, and in all 3 of our cases of our effect sizes that we produced, we do not have any considerable effect sizes. Alright, I think that's about it. Thanks.